Hi, can everybody see me? Is everybody there? Hello?
We can hear you.
Okay, wonderful. Okay. Hopefully it'll be stable now. I've got a plug, Ethernet plug hooked into the computer. So basically, as I was saying to the other students, the worksheets, those of you that did the worksheets, please bring them by my office after class today, and I'll check them in. I just want to look over them and see how you folks did with it. The whole point is to get you some practice before the thing, and basically I was looking for completion and you to show the work. So basically we're going to go forward from here. Are there any questions based on what you did over the weekend? Anyone? Anybody here? Any questions? Okay, very good. So let's continue where we left off. Now, what I'm going to do is continue with chapter 4 and the Chang thing, and I highly recommend you continue to use that one. Again, the chapter 4 for our book in the PowerPoints is just a bunch of charts, and I'll kind of back up with that as we go through. But the big thing I want to do now is just continue where we left off with it, just so you can get things in context regarding how these things work. So let's move to where I stopped. Okay, let's go here. Now this is the acid thing. Okay, I'm going to share the screen with you folks. Please let me know that you can see it. Okay, can everybody see the screen? Can everybody see the screen?
Yes.
Okay, wonderful. So let's continue. And basically what I'm going to do now is define them. I did it before in the lecture portion for the lab, so I'll do it again. Yes, question? The testing will be a week from today. I'm going to finish chapter 4 this week and basically finish chapter 4 this week. I'll have another take-home worksheet for you to work on over the weekend to prepare, and then the test will be on a week from today at either 7 or 8 o'clock. For those of you if you have something happening at 7, you athletes, can you come at 8? Okay, so we'll do the same way as before. And those of you distance, if you came before at 7, please do again. We have how many athletes? Okay, we have 5 athletes, so basically 5 people from the other group can come just like you did before. So it should work out just fine. And we'll have a rolling thing. You just come in at 7, and then when the people are done, then if there's a line, the people can come in and replace them as we go. So what I want to do now is kind of define acids and bases, just to put things in context again. Sorry, I need the mouse. Okay, I'm going to define acids and bases first. And we're going to use, there's 2 main definitions. I talk about the Arrhenius ones in lab, and I'll use that again. But basically, if you have a solution in water, it gives hydrogen ion, okay? A base is a solution in water, gives a hydroxide ion. Yes. Someone had a question? Hold on a minute. I want to make sure this is recording just a moment. Okay, yeah, it is recording. Good. Okay, just wanted to double check to make sure it's recording. Okay, basically, it gives hydroxide ion. This is the definition of base. Oh, sorry, let me go back. A weak acid or base is partial dissociation, partial breakup. An example of that is what you did in lab before with acetic acid, which looks like this. And essentially you add water to it, and you get the H plus the acetate, CH3COO minus, but most of it is on this side. So this essentially stays in this form over here as well. So you've got some of this still there. That's how you can smell it. Okay, and if you have a weak acid, there are all sorts of weak acids that you can smell. Okay, and they're particularly in the area of stuff like acetic acid that has a certain smell to it. Bigger ones like citric acid and whatever are solids when they're dissolved, so you can't smell them, but you can taste the acidity when you taste it. Properties of acids: they have a sour taste. Vinegar owes its taste to acetic acid, and also vinegar also owes its taste to the fragrance. There's various aspects in it too as well. Okay. The color changes in plant dyes. That's what phenolphthalein is. That's the whole concept of indicator that we did in lab. It reacts with certain metals to produce hydrogen gas. And you saw that with the hydrogen lab we did before, where you took the zinc, you did it online with this, but HCl goes to form zinc chloride in solution, aqueous, in the presence of water, of course, plus hydrogen gas. So essentially you can have, the hydrogen comes off to do that. Sodium is also another example of something that forms with that as well. Basically that gas will burn when that occurs. Okay, and an example of that is HCl with magnesium, and it gives off a gas. And again, they're both represented as aqueous there. Reacts with carbonates and bicarbonates to produce carbon dioxide gas. That's the whole mechanism of baking soda. If you take a half teaspoon of baking soda for an acid, the acid that's in your stomach is hydrochloric acid. And basically the purpose of the antacid is to neutralize some of it, so you can essentially feel better, okay? And that's usually due to reflux of a little bit of acid that goes up into your esophagus area. Another example there is the calcium carbonate there giving off carbon dioxide and water. Aqueous acid solutions conduct electricity. They are electrolytes, as we talked about before, okay? Properties of bases: they have a bitter taste associated with it. They feel slippery. Many soaps contain bases. Okay, and believe it or not, that's part of the reason that dark roast coffee has a relatively bitter taste. It's because it has some, and why people like to add milk to it is because it has acidic and basic properties associated with it. So the taste of the things, the acid quality of coffee comes from whatever is extracted from the coffee bean, the roasted coffee bean. And bitter is often part of that. It causes color changes in plant dyes. That's what you saw again with the indicator. And aqueous-based solutions conduct electricity as well. So ammonia and ammonium hydroxide there. Arrhenius acid is a substance that produces hydrogen ion in water. And this is essentially the thing that happens that I showed before. Arrhenius base is a substance that produces hydroxide. The hydronium ion is a hydrated proton. And basically, in reality, there is no such thing in solution of the H plus. Aqueous, that doesn't exist, but because the water molecule is not really involved in the reaction, it's just a carrier, it's essentially ignored. And I prefer chemistry textbooks that use H plus instead of the H3O plus. All that tends to do is clutter up the page, and it's really not involved in the reaction. Excuse me. I'm sorry, that's allergy related. I've got postnasal drip, so unfortunately it happens. Brønsted acid is a proton donor. Brønsted base is a proton acceptor. And some examples of this where you get a proton from the water molecule that goes to the ammonia. It donates a proton there, and you get ammonium hydroxide when you dissolve it in water. That's the acid, the base there, and then the other side as the acid and base on the associated side. The Brønsted acid must contain at least one ionizable proton. Monoprotic acid, there's a bunch of different examples of them. Hydrochloric acid is one, it's a strong acid. Nitric acid is another. Acetic acid is a weak acid, a weak electrolyte. Diprotic acids, that would be two of them. And if you continue, this will go to form, again, another H plus SO4 minus 2. So there's two of these involved. So you have two of them that come off of it. It's a strong electrolyte with a strong acid associated with this. And so essentially you have both of them working together in this relationship. And please ask questions if you have any questions as I go through this. This is kind of summarizing what's in the book and in your reading. So please read along with these as well. I believe Hein does talk about acids and bases in chapter 10 and 11 if you want background for that too. So I encourage you, particularly those of you that did not have high school chemistry, to read those chapters related to acids and bases. Triprotic acids include phosphoric acid, weak electrolyte, weak acid, and essentially it gives three of them associated with it. And then there's a chart for each of them. Okay, now let's go through these. What is A? Is A an acid or a base or both? Anybody? Is A an acid, a base, or both? A right here. Is A an acid, a base, or both? It's hydrogen iodide. Is that an acid, a base, or both? It's an acid, okay? How about the B? That's acetate. Is that an acid, a base, or both? No, that's acetate. It's already gotten the thing off, so it's the base. It's the base part. That would be in, for example, sodium acetate. Okay, that's the basic portion. And when it's missing that thing, it's just like OH, okay? It just happens to be a weak base, yes. Well, basically, if it can give off a proton like that, it's an acid, okay? But if it has an O with something else on the other side, this is a base. It's a proton acceptor, so it'll grab the extra hydrogen to go back to the original form. It could be hydroxide, it could be this one as well, okay? So basically, it's just a matter of understanding how those things, proton acceptor, proton donor. If you look at these here regarding proton donor, the HI would be an acid. The proton acceptor is the base there. It can grab and it will become acetic acid like this, right? It grabs the proton. You understand?
How do you know if something will give off?
Well, usually if it's a full electrolyte, like hydrochloric acid or some other thing like that, and it's usually based on what its structure is and the strength of the bond. If it's more ionic one like HCl, then it will give it off. But if it's like ethane, it's considered, and you'll learn that in organic chemistry, it's considered a very, very weak base, only an acid, only under extreme circumstances, because it's not likely to give up that extra hydrogen because the bond is a different type. Okay, so when you have a salt and you have available hydrogen, like citric acid, acetic acid, or hydrochloric acid, it gives off that extra hydrogen. That's just a proton donor. It has to do with the weakness of the bond, and we'll talk about bond strengths a little later in the semester. Okay? So right now we're just going through a list of understanding how they work. C would be both. Why? Now there's two hydrogens there. Well, it can lose two. Okay, basically, let me show you. You put it in this form, H2PO4. We'll break off and get an H plus HPO4 minus 2. Okay? It lost one.
How would we know that?
Well, just you learn it gradually. This comes later, particularly in general chemistry too, where we get into buffers and other things like that. Okay, this is kind of an introduction to acids and bases, and the main ones you need to know about are nitric, acetic, hydrochloric acid, and phosphoric acids, that kind of thing. Okay, and how can that accept a proton? What happens if it accepts a proton? No, it'll accept a proton. It'll go here, like a hydrogen proton, and essentially it'll go to form this. Again, the original phosphoric acid that we started with. That essentially is going back the other way. That's how it accepts a proton. It goes back. And you'll understand that more later when we get to the bonding and such like that, the nature of the structure of those molecules. Okay? Did that answer your question, sort of?
There's not really there's not like there's a clear way to identify it.
Well, if I go a little ahead, this is what phosphate looks like, okay? So essentially this is the bond, and it has all these electron pairs around it, and you're gonna learn that a little later. But all these electron pairs can grab a hydrogen and form a bond. That's one, this is the other, this is the other. So that's H3PO4. Okay, it's a little complex, but that'll become clear later. So all I'm asking you to do is just trust me, quote unquote, it'll become clear later. But what you need to know about now is just HCl and the nature of things based on what the lab we're doing this week is, and those of you that did it last week, okay? Please don't overthink it, but many of you are thinking about where it's going with this. And that, particularly those of you in or biology majors or biochemistry, you'll get a lot more into organic acids and bases later, okay? There's a whole lot of different, examples of them. Okay, this is a Brønsted acid. This is their better graphics. See how it gives up the hydrogen, okay? Here, it's a Brønsted base. It grabs one, okay? And here, it can give up a hydrogen, just like I showed you earlier, okay? Or it can grab one and go the other way. So it's both. Does everybody see that sort of better now? Any questions? Nicholas, do you understand this? Nicholas?
Yeah, somewhat. I'm getting the hang of it.
Okay, good. Okay. And again, please do the reading and work the problems within the chapter as you go through this material. Now, the neutralization reaction, this is the reaction of an acid with a base. And essentially, an acid and a base, you'll get salt plus water, okay? And basically, we discussed that a little bit before in the lab introduction, of which some of you are going to see this week. But basically, the acid would be like HCl. The sodium hydroxide will be the other one. These are both aqueous, okay? Goes to form sodium chloride, aqueous, plus water, liquid. Okay, that is essentially the what's occurring in the reaction between sodium hydroxide and HCl, of which you're titrating, sort of using the acetic acid in the lab. You're just using acetic acid and sodium hydroxide in the lab, but there's really essentially no difference between both of them, and you get a solution of sodium acetate plus water again for that one. So essentially it's the same thing, that just in the lab we're just using acetic acid just because the professor decided to use that. There are other general chemistry 1 labs that have just reacting hydrochloric acid with it, but this is a good one because it has a nice smell of vinegar too, and you can kind of see and learn a little bit more about salad dressing and other stuff you've had that would have a tangy taste associated with it. Okay, so here's the full equation. This is called the molecular equation, molecular. This is the ionic equation. What is common to both sides on the second one? And these should all have aqueous next to them. Aqueous, aqueous, aqueous. What's common to both sides on this second one? The chlorine, what else? The sodium, yes, very good. And then at the end, okay, you get the neutralization reaction. This is called the net ionic equation. Now, when we did the precipitation reactions in the beginning of the chapter, for the slides for the beginning of the chapter, it's a little elsewhere in chapter 4 in your textbook, but you can read that also. There are also net ionic equations for that, like say, for example, silver nitrate plus HCl goes to form silver chloride, which is a solid, plus the acid NH3, which is aqueous now, and essentially you have a net ionic equation there too. Ag plus Cl minus goes to form AgCl solid. So essentially those are the ones related to it. This is the PPT reaction or precipitation reaction. And that's discussed a little later in the slides, but we already introduced it in the previous ones, okay? So basically these work together here related to both of them. Neutralization involving a weak electrolyte. Well, hydrogen cyanide is an example of a weak one, and another one would be the acetic acid that you've done before. So acetic acid is also one related to this too. Okay, this is acetic acid. Okay, and essentially you form the sodium acetate over here as well, plus water there. So essentially, this is what you did in lab regarding these. And you get a salt and water also. Yes?
Like, what does it matter if it's strong or
Well, basically, strong or weak acid, a weak one will conduct electricity a little bit. The light bulb, the light bulb will just be a dim lit part, and you'll be able to smell it or whatever else, like in the case of the vinegar. Okay, but with HCl, particular things, you can't smell it. Like a 1 molar solution, you can't smell it because the hydrochloric acid, hydrogen chloride gas is dissolved fully. And gradually you'll get to learn those. But basically with these, you have a partial relationship to both, and it goes in both directions with these. So there's partial reactions. Neutralization involving producing a gas. An example of that would be HCl plus sodium carbonate goes to sodium chloride, or you could have sodium bicarbonate here, which will also give one out, okay? And with sodium bicarbonate, you only have one of them associated with it. And basically you'll get sodium chloride again, plus H2O plus CO2, and that's essentially what's in baking soda is the bicarbonate there. So essentially, there's a bunch of different ones that'll produce a gas with a neutralization reaction. Okay, and then again, you have the ionic equation, and then you have take out the extra parts, and you have that as being the net ionic equation associated with this, and this is a gas, again, related to that. You have the acid, the base reacting to give water, and the gas there. Okay, so basically I'm going to stop with this slideshow and go to the other one briefly. Okay, I'm gonna switch slides now, people. So we'll go to the other part. Okay, I'm going to share the slides now again with you. Okay, can you see the slides again, people?
Yes.
Okay, so basically, when you're dealing with solutions, essentially you have two things associated with this. When you have a solution, you have the solute and the solvent. And the molarity is how you determine how much is in each. Because if you were to take grams of a solid and react it, you would go to moles of a solid, okay? So in the case here, when you have the number of moles of a substance, you go grams of a solid to the moles dissolved when you're dealing with the material. So essentially you have dissolved in each liter of solution. And again, the solvent in this case, the major component is inert. It's not involved in the reaction. So basically it's just a medium for carrying the solid material that you're reacting it with something else. And the molarity is what is concerned regarding each of these. Okay, so the solution concentration, the molarity, you take a measured number of moles of solute, and it's usually in the form of grams. Enough solvent is added to dissolve the solute by swirling. The further solvent is added to get it to the calibration mark, and then you've got the solution, and in this case they use a yellow solid in it, and that will have a certain molarity associated with that, and this would be moles of solute per liter of solution per liter. And so basically what that does is it makes it easy to measure out a certain amount of moles of material, because you just use a burette or a pipette to get the precise amount of material into the beaker or the reaction flask when you're doing it. The molarity converts between moles of solute and liters of solution. There, for example, 1 mole of sodium chloride is placed in enough water to make 1 liter of solution. That'll be a 1 molar solution like that. And essentially, that is essentially what you use to determine it. And like, for example, how many grams of solute would you use to prepare 1.5 liters of a 0.2 molar glucose solution, 0.25 thing there? And again, with these, you have these things related to them going for the other way, where you have 1.5 liters. You have this part here, the 1.5 liters from the original problem. You put the molarity there times that, and essentially that uses the form of the molarity times the volume equals the molarity of the other one times the volume there, because when you're dissolving, you have moles goes to moles. Moles equals moles, and essentially you have the relationship there, and you essentially divided both sides by V2. That's what you're doing in the lab when we do this, when we do that this week. And for those of you that did it last week, this is called the solution concentration, the molarity in that situation. Okay, diluting concentrated solutions, essentially you have the initial one related to it. Since the moles of solute remain constant, the only thing that changes is the volume. And so in this one, you have other things related to that as well. And basically these this is used for that same thing. And then you're just putting moles in the liquid medium into this, adding more liquid to it. You still have the same moles in the flask, right? The only thing you're changing is the concentration. So it's just a matter of, it'll change the molarity in there, not the amount of moles of material. And then there's a sample problem related to that. So that's kind of an introduction to the math that's involved with these diluting concentrations of these. So I recommend you read this portion of the book, and then go through those sample problems to help you understand how the math is used in these forms. Okay, now electrolytes in aqueous solution. Substances dissolved in water to produce conducting solutions of ions. We talked about those also. And non-electrolytes, there's an example there of sugar dissolving in water. And again, this is how you can tell a weak acid from a strong acid, okay, or weak electrolyte, and they show a little picture, and then they give a chart here related to this. Precipitation reactions. This was talked about in the previous slides. And essentially you take one solution like this and another one. This is AB plus CD goes to CB plus AD, okay? And this is called a double displacement reaction, okay? The next one, acid-base thing that we were just talking about also, going from HCl and sodium hydroxide, and then oxidation reduction reactions, which I'll talk about in the next section. The molecular equation is when you have all the substances and the chemical things are written using their complete formulas as if they're molecules. This is the molecular equation. And how would you move this to the ionic one? Correct. You essentially break these up into its pieces. So essentially this would be lead plus 2 nitrates, aqueous minus plus 2 potassiums, aqueous plus 2 iodides, aqueous minus goes to 2 potassiums, aqueous plus nitrate, aqueous, 2 of them. And then you have lead iodide there, and this is a solid, a precipitate. That's the molecular equation. The ionic one, you've essentially broken them down. What's common to both sides? Yep, potassium. Okay, and the nitrate. And then you get with the net ionic equation at the end. So these are essentially removed. They're the spectator ions that were shown earlier. And the net ionic equation is what occurs. And the precipitation reaction is the same kind of net ionic equation as you have with the acid bases that I was talking about earlier in the class today. Solubility guidelines. When we have solubility questions on the exam for number 4, I will provide this chart for you. I don't want you to memorize it. I want you to, I will provide a little chart. It's just a matter of sort of using the chart and figuring out which ones are soluble and which ones are not. But for example, the group 1A cations, these are almost always soluble, as is ammonium. Here, it's probably soluble if it has these associated with these, the anions associated with it, except for when it has these kind of compounds. And then the nitrates, chlorates, acetates, sulfates, etc., except for heavy metals. Heavy metals tend to be insoluble when you're dealing with those things. And this is a chart. This is a chart that I may that would be provided for you if we had this kind of question on the exam coming up. Okay, so I don't want you to memorize the chart. I just want you to be able to use it. So again, it's just a matter of when you're working the problems in the chapter to just practice these and see how those things go with it. Write the molecular and net ionic equations for the reaction that occurs with aqueous solutions of silver nitrate and sodium carbonate. You had a question?
Yes and no.
Okay.
I don't understand what kind of problems you can do.
Well, they're giving you an example here. This is the table you look at, you print it out. You print out a copy of this, okay? Then you try this next one. Aqueous solution of silver nitrate and sodium carbonate plus sodium carbonate. What would you look for in the previous chart? Right, you look for carbonate on the previous one. Where's the carbonate? Yeah, so they'll be insoluble. So what does that tell you when you have those two ingredients? And if you remember this form, these are an AB plus CD goes to AD plus BC plus CB, okay? It's a double displacement reaction. So what's likely to be the insoluble one? Because you have the silver there and the carbonate. So what's going to be the insoluble part? Yeah, the silver carbonate. So this will be the insoluble one. A solid. That'll come out. Okay, so you will put those pieces together when you do that. So that's how you use the chart. You look at the thing, look at the chart, see what fits, then put the pieces together. And I do not want you to memorize that chart.
That's the complete answer.
No, not quite. That's my handwriting. I'm just introducing it to you. Because I'm trying you look at this one. You see the silver and you see the carbonate, right? You go to the previous slide. Notice the carbonates here. And then the silver ones, the silver's over here. Silver is, a lot is in all of these. But when you have a carbonate, it's always going to be the silver. That's the other one, because what is the other one? It's sodium. And they're almost always soluble. Okay? You see the sodium there?
That's not what I was asking.
Okay.
When you were doing and like you were the solid underneath, that's the complete answer to the problem.
Well, sort of. Sort of. The complete answer of the problem is the net ionic equation is this, 2 of them, plus the carbonate, minus 2, aqueous, goes to silver carbonate, solid. That is the net ionic equation. Okay? So you write the chemical ones related to this. Write the chemical formulas of products using proper ionic rules. So again, we have double displacement reaction or double reef placement. This is what I was showing you with the AB plus CD. goes to CB plus AD. And your book goes into this as well, okay? As does Hein with a little bit more detail. The second one, you have the molecular equation. Which one, neither the cation nor the anion is in the solubility list. This one has the group 1A cation. This is the group 1A cation right there. So you kind of put it in that form first and figure out which is going to be the insoluble one. And in this case, it's the carbonate. So the cation nor the anion is in the solubility list. That's the molecular one. And so the ionic equation, you disassociate the parts. What is common to both sides? What is common to both sides? The nitrate, very good. What else? The sodium, good. And now you have the net ionic equation at the end. That's the net ionic equation. Now, where does the stoichiometry come in? Okay, say you add 30 milliliters of 0.1 molar silver nitrate, 30 milliliters. You add 20 milliliters of HCl to it, of HCl. And let me go out of the slides for a sec. I want to draw an example here. Okay, I'm going to draw an extra slide in here, folks. Just a minute with this. Okay, what I'm going to do now is give an example of how the stoichiometry that we learned in chapter 3 is this. Say we have, say we have 30 milliliters of 0.1 molar silver nitrate. We add 20 milliliters of 0.1 HCl, aqueous. Okay. How many grams of silver chloride result? Okay, so we start off with the thing. What's the first thing we can do? What's the first thing we do with this kind of problem?
Change it so you do your moles to
No, before that. First thing we do is put down what? Yes, the equation. So let's put it down. Silver nitrate plus HCl goes to silver chloride plus HNO3. Okay? What is the net ionic equation for it? What is the net ionic equation for it? Well, again, it's the same. HAG plus aqueous plus Cl minus aqueous goes to silver chloride, aqueous, solid. Okay? So, Nick, what's the next thing we do? Nicholas, what's the next thing we do? You started that. Now, after we have that formula down, what's the first thing you do? Nicholas. Oh, I'm sorry. Nicholas, what's the first thing you do then?
You cancel out the things that in the equation on both sides.
Right. But to
like
solve this problem, we've got the equation down here. Everything's been canceled off right here. So after this stage, what's the next thing you do? You convert what to what? You convert it to moles.
Convert it to moles. Yeah.
Okay, so we have 0.03 liters of silver nitrate, right? So we
Yeah.
of 0.1 molar. So essentially you have 0.03 liters. Well, I'm going to go back here. We have 0.03 liters of the 0.03 liters times, what's the molarity? It's 0.1 molar silver ion, right?
Yeah.
So now that'll convert to moles, right? So this is moles per liter. So that means you have 0.03 with a 0.1, so it's 0.003 there, moles, and that's moles of silver ion, okay? And then you look and see it's a 1-to-1 relationship between that also, so that means you have the same amount there of silver chloride. You then figure out based on the molar mass of silver chloride to find out what it is, okay? So that's a sample problem that might happen with that part of the reaction, okay? So basically, this is the kind of sample problem you'll get into with your homework this evening regarding going from what we learned in chapter 3 to the stuff you need to know for chapter 4. Does that make sense to you, Brendan?
So how did you go from like the AgNO3 plus HCl, you like canceled out?
Yeah, you went to the net ionic equation like before, right? It's already balanced. I kept it simple. It's already balanced here. We then canceled it out, went to the net ionic equation. That's the part that's reacting.
Okay, so you can just cancel stuff out.
Right, and now you've got the last thing here, and you use the M1V1 equals M2V2 thing, essentially to do that, to determine the moles of each. Okay, and then you can go to grams of product. And I'll go with some more examples of this. I just wanted to introduce this for you for the next time. Okay, any questions of those that are virtual? This is like an introduction to next time. Any questions?
Do we do anything for Wednesday?
Yeah, just continue to work on the homework problems of chapter 4 related to what the lecture was today.
Sounds good.
Okay, so I'll see you all on Wednesday. Thank you.